Hi guys, how's it going? So today we're going to be going through the transform architecture. So I thought it would be a good idea to kind of like walk you guys through the code and explain each line of code and the intuition and the idea that the authors had when they were building the transform architecture. Most importantly, walk you through each line of code, explain the why and the how they did it. So I thought that'll be good so that you guys can actually understand what's actually powering some of the modern systems such as ChatGPT. Definitely language model will have a huge impact in building modern systems. So understanding some of these architectures such as transformers will actually help you to kind of like understand some of the modern papers that have been written today. So without wasting any time, let's get into it. So now we're gonna get into the transform architecture. So I thought it would be a good idea for me to kind of like give you guys a high level overview so that you understand the architecture of the transformer. As we go through the code, you will understand where we are currently at. The transformer code can be quite lengthy, so I thought it would be a good idea to kind of like explain the portion that we're currently coding, and we're gonna keep coming back and we're gonna keep revisiting these architecture, and we're gonna see what's going on inside each component in more detail. So this architecture essentially is divided into two. So we call this part, the left portion, we call this the encoder, right? And we call this right part, we call this the decoder, right? So the decoder, essentially what it does, it tries to map the input. So you can think here we have some sort of like a sentence in English, right? So we try to map that to a continuous to a sequence of continuous representation, right? So we take that continuous representation, we feed it into the decoder on this multi-head attention portion, right? The decoder, on the other hand, receive the output of the encoder output, so together with the decoder output at the previous timestamp. So the decoder uses the output that it generated previously as input along with the output of the encoder. Okay, so you have two things here coming in the decoder. You have like the previous timestamp output, and you also have the output coming from the encoder. Okay, so stick with me. We're going to explain why they're doing this. Like I said, I promised you that I'm going to explain the intuition behind this. For now, I just want you to kind of like understand what's going on at the high level. So in the paper, they replicated this portion here 6 times. So we can think of this as one layer. So we call this encoder stack. Encoder stack has we replicate these layers 6 times. Okay, so a single layer, right, has what we call sub layers, right? So what do I mean by sub layers? So I mean looking at this layer, it is like the multi-head, as we can see. Sorry about that. Actually, let me try to zoom in, guys, for you. But we have the multi-head, we have the feed forward. So we call these sub layers within this layer. So then what is the first layer doing? What is the first layer, which is the multi-head? So I'm talking about this portion here. So this portion here, that's the first sub layer within the first layer. So is the multi-head implementation. So what it does is that it receives a linear projection of the query keys and values. So multi-head, and it receives. So I'm gonna explain what these query key value means and what they do and what's the intuition behind these. Then the second layer, not the second layer, the second sub layer, sorry, second sub layer, which is this portion here. We call this the feed forward. So this portion here, so that's like the feed forward portion. So it consists of a linear transformation with a ReLU between And how we can represent this, we can think of like we have a fully connected layer, we have ReLU, this ReLU, then we have YI, maybe BI, something like so. Then what we have here, we have these residuals connections. So these connections that are connecting here, and we have norm, I have another second residual connections. So what we can say ultimately is that these sublayers have residual connection, right? That's one thing that we're seeing here, residual connection. And the sublayer consists of normalization. Okay, so what kind of normalization? We're using a layer norm. Okay, so we're using a layer norm. So you can think of this layer norm, essentially it's gonna take x plus, which is the residuals, then we take the sublayer output, right? We add to this is the residual, then we cover this by the layer norm. Okay, so why are they using the layer norm, right? So the layer norm essentially try to estimate the statistics of the sound input to the neuron within a hidden layer. So also it helps us to not introduce dependencies when we training, right? So it's quite a powerful normalization technique that we need to use, especially when we're working with sequences, and that's why we can use something like batch norm in this case. Okay, so let's look at another component. So we have this component here called positional encoding. So what does it do? So transformers essentially do not have recurrence, right? So unlike recurrent neural network, therefore it will be hard for them to capture the position of its weight, right? Like when we work with sequence, each weight in a sequence have some sort of like a position, right? So how do we then capture the position of this weight? So we use positional encoding, which we're gonna get in more detail. Then we're gonna explain how does it work and the maths behind it, and how does it enforce positions within the sequence of weight, right? So we're gonna get into that, but that's another component. So now let's look at the decoder portion, right? We explained the encoder. Now I'd like to look at the decoder at its sublayers. They're the same, they use the same component, slightly different implementation, right? So the first sublayer, this sublayer of the decoder, essentially receives the previous output. Yes, here we receive the previous output of the decoder and augmented with the positional information, right? We apply the positional encoding, and then we push these things into the multi-head attention with the first, which is the sublayer. So with the encoder, what's the difference? And with the encoder, essentially we attend to all the weights in the input sequence, right? Whereas the decoder looks only at the previous weights or preceding weights, right? So essentially this decoder here is unidirectional, right? That's what they said. So in the multi-head, this is achieved. So in this component, the sublayer, this part here, we achieve this using the masking function. So the masking is what actually help us to have this unidirectional functionality of this. So I'm just going to erase these so make it a little bit cleaner. So what you're seeing here, we have 3 inputs that are going into the sequent. So we can think of this as the sequent sublayer, right? as the second sublayer. So these three inputs. So here we have the queries of this going inside the multi-header. Then we have the keys and the values. Like I said, I will explain what these are when we get to the attention. And yeah, when we get to the attention portion, we're gonna know what these values and key, what they mean, the intuition behind this thing. So essentially, the second layer receives the queries from the multi-head, and it gets the keys and the values from the output of the encoder, and that's how it works. So, but I hope that kind of like gives you guys high level overview, and like I said, each and everything we're still gonna get into more detail. So now let's go to the code and try to code this, and yeah, we're gonna keep coming back and show you guys where we are, and yeah, let's go. So now we're gonna go through the code. So what I've already done is to just import all the libraries that we're gonna need and made necessary installment from the Spacey library. Some of these libraries we're gonna be using them in the training portion. So the first thing that I'd like us to do is to have a high level architecture. So we're gonna say architecture. We're gonna have the encoder and the decoder, and we're gonna inherit from the module. Then initialize. So we taken the encoder and encoder architecture. It takes the encoder, it takes the decoder, and we're gonna take the source embed, and we're gonna have target embed. Then we're gonna have the generator embed. So what does this? So this is the encoder, this is the decoder. So we're gonna code these things up, so we're gonna understand them. So the source embed and the target embed, so essentially they embed the input sequence into a continuous vector space. So they do that using the embedding matrix. Okay, then with the generator, essentially this is responsible for the final output of the model by so it applies the linear transformation in a softmax output to the output of the decoder. So that's what it does. We're gonna then take the self dot encoder, encoder equals to encoder. Then we're gonna take the self dot decoder equals to decoder. Then we're gonna take the self dot src, which is source embed, equals to source embed, self dot target embed equals to target embed. Yep. So now we take a closer look at the encoder. So the encoder, it's going to take in the self, and it's going to take in the source and the source mask. So the purpose here is that the encoder is responsible for encoding the input sequence into a fixed representation, and we can think of that fixed representation thing as a context, right? And it also takes in the input and the mask, like here we're showing. So this is to indicate which element should be ignored. But I think this source mask is optional. So in the architecture, I think on the diagram they have that OPT thing to show that it's optional. Then we gonna return self dot encoder, which is going to take in the self dot source embed. So we're gonna embed the source, the input rather. Then we pass in the mask, so just source mask, like so. And now we have the decoder, okay, which is self. We're taking the memory, we're gonna take in the source mask, we're gonna take in the target, we're gonna take in the target mask. Okay, so what does the decoder mean then? So the decoder takes the encoded representation from the encoder and generate the output sequence, right? Not only that, it also consumes the target sequence and mask for both the input and target sequences. Okay, so what I mean is that actually let's do the self.decoder. So we're gonna take in the self.target embed. So that's gonna be embed, which we're gonna take in the target, then we take in the memory. Yeah, I think this memory is coming from the encoder as key and queries, but we're gonna get into that if I'm not mistaken. Yeah. So we have mask, and we have target mask. Okay. So the only missing piece here, I hope I did not miss anything. Let me just remove this portion here. Yeah, so we embed the target, and we take in the memory, we take in the source mask and the target mask. Okay, so we have the forward pass. So we're gonna take in the forward pass, which is self, source, and target, and also we take in the source mask, we take in the target mask. Then what we do is that we return the decoder, self.decoder, which is self.encode, we take in the source, and we take in the source mask. Then here we're gonna take in the source mask, and we take in the target and the target mask. Okay, so this is a high level overview of the architecture, and we're gonna keep on coding these things in more detail as we go forward. So yeah, let's continue. So before we forget, let's initialize the generator. So generator, and we gonna create a class of the generator. Okay, so before we create a generator, I want to talk about why we're creating a generator and what is it, right? So the generator essentially is used to convert the final output, right, of the decoder into probability distribution over the vocab. Okay, so this essentially allows the model to make prediction about the next word, the next token in the sequence. So if we go to the architecture, so we essentially talking about this component right here. Okay, so that's what we're gonna try to code. So we're gonna take from the NN module, and we write def init, and I'll actually appreciate it, guys, if you can tell me if you enjoy me just writing the code, or you want me to pre-write the code, just explain what this code mean, or you just want me to code it up. So yeah, so I'm still new to this, so I'm trying to understand what you guys actually prefer, so it will be nice if you give me feedback. Anyway, here we take in the dimension, then we take in the vocab. Okay, then we're gonna say super generator, and we take in the self, then we're gonna say dot init. Okay, init. Okay, so we have dimension of the model and the vocab size. So we're gonna project this into, we're gonna create a linear function, and we take in the D model, which is the dimensionality of the model, then we have the vocab size, and that's it. So now we create a forward pass, which is going to take in the self and the input, right? Oops, self and X. So what we're trying to do here is that we're trying to take the vector of real numbers, and we're going to return the probability distribution. So we use the log softmax to make the loss stable and efficient, right? So we return the log softmax, and we take the self.project x dimension equals to 1. Okay, and that's our generator. So now let's look into the encoder portion and all its sub layers. Okay, so we're gonna say, let me just do this because there's more code that it has to go inside here. So I think it's better if I kind of comment it out. So we're going to have def clones. So the encoder, as like I mentioned when we were in the diagrams, so it consists of like n stack. So that n is 6 in the paper. So these stacks are identical layers. So we have to clone all of those n stack. So here just produce n identical layers, So then what we do is that we just gonna return nn.module list, and we take in the copy dot deep copy of module yes for in range of n. Oops. Did I miss something? Okay, I think the in has to be there. Yeah, so that's fine. I think here we have to take module. I made a mistake. And we're gonna keep on adding to these. I'm gonna show you how we're gonna do that. But we're gonna see all our sub layers, like the multi-head, the feedforward. We're gonna keep on appending them to these stack. So you will see when we go through. So the encoder portion. So we're gonna have the encoder. Don't confuse these two components with this. So you can think of this as a high-level architecture, like the encoder decoder. So we have to code these components here, like the encoder, decoder. So we have to work our way to these. So each component has a set of sub layers, like I said. So it's quite lengthy. So you can think of this as a skeleton. And what we're doing now is that we're trying to write more the component each, right? So yeah, just know that. So we're gonna take in from the module, okay. Then we're gonna say def. So one thing to keep in mind, like I said, that we produce n identical layers. So even with the encoder, so what we do is that we try to produce n layers, right? Then within that n layers we have sub layers. Okay, so what I'm going to do now is to initialize this. Then I'm going to take in the self and layers and n, which is going to tell me the n layers within the encoder component. Okay, so I'm going to have super encoder. Okay, so I'm going to self dot net net then I'm gonna say self dot layers equals to clones. So take the layer, right, and pass in the number of layers. So you can see that it's gonna say for that number of layers. Let's say for instance it's 6. Then it's gonna copy this layer. You see here 6 times. So it's gonna copy. It's gonna do good. So that's what we're doing is in this case here. So that's why we pass in the layer and we call this layers. That's why we return. Okay. So that's what it is. So what do we do now? Before I continue, I'm gonna keep on repeating this once again. So the encoder, right, is a stack of n identical layers, right? So this portion here, right, this let's go to this portion. So we repeat this part on the left, this component 6 times, right? We can have another one here, can have another one here. Okay, so that's what it is. So each layer essentially is going to take the input sequence and it's going to apply the same computation, and then that output is going to go to the next layer, right? So after we go through each layer, the final output has to go to the layer norm, right? Let's look at the diagram, right? So you see here we have a layer norm, right? So that's where the final output is gonna go into. Okay, so yeah, so layer norm is gonna make sure that it normalizes the activations before it returns the output. Okay, so which means that now what I want to do is that I'm gonna create that norm. So it's gonna be self.norm equals to layer norm, right? Then I'm taking the layer dot size, then what we're gonna do is that we're gonna do the forward pass, forward. So we're gonna say self x and mask. So we're gonna say for layer in self dot layers. Okay, then we're gonna say take the layer and pass in the input and the mask, and then this will return the x as an input. Then what we need to do is that we take that x, we normalize it, so we can say return self dot norm x. So class, actually before we continue, let's go back to the diagram. So essentially we coding this norm and this residual connection. So this is what we're working on, this creating this class or this function for these two components, right? So just reminding you where we are. So we have layer norm, and we go to say nn dot module. Okay, then we say def init. We take in the self, we take in features, and we take in epsilon. Okay, so what is this? What is this, right? So we can think of this as a small positive number So it's added to the variance of the activation before we take the square root. So you're gonna see this a lot, so we write this also to prevent the division by 0. I'll show you where we use it, but yeah, that's why we need it. So what we have here is that we're gonna actually say super, then we have layer norm, layer norm self dot init. Okay, do I have an error? Okay, no, we don't. So we good. So we're gonna say self dot a2 is gonna be equals to nn dot parameter. I'll explain now what this is. Then we're gonna say touch dot once, and we have features. Okay, so when we have a layer norm, we have learnable parameters, right? So we can think of this learnable parameter. So it actually it represents the scale factor of the normalization, right? So some people say that it control the strength of the activations, right? So all the things that I'm saying I'm gonna try to document them. So then I'm gonna put them into GitHub so that you guys can reference everything that I'm saying. So you don't have to worry about if I said something and you missed it or anything like that. So I will basically document everything. So we have parameter and we have touch dot zeros features. So here we control the bias. Okay, so this is the learnable parameter also, but then it shifts the factor of the normalization, whereas this the one with ones, it controls the strength of the activation, so it scales the factor. So right, so that's what I've learned about these two parameters. Same, we're gonna say self dot epsilon equals to epsilon equals to EPS. Okay, then we have a forward. Then what we do is that we're gonna say self, we take the input, okay, then we say mean. So that's how these normalization techniques work. We take the mean divided by standard deviation. So here we're going to take the mean of x, then we -1 keep dimension equals to 2. Okay, hope you guys are still with me at this point. We have standard deviation. So we have x.std, we have -1, and we have keep dimension equals to 2. So pretty much this is how we kind of like normalize, I'll say. We take x, we subtract the mean from the input, then we divide by standard deviation. Okay, so but this time we have also learnable parameters. So we're gonna take self.a2, which we said was the this parameter that actually scale the factor of the normalization. So it kind of like control the strength of the activations. Like I said, we take x minus by mean, and then we gonna divide by standard deviation. Standard deviation, then we add the self dot EPS to that, then we add the learnable parameter which control the bias, right? So it's gonna be B2. Yes, I think, did I make any mistake? Yes, I did, which is here. Right. Yeah, think now it's fine because it's not supposed to be self. We define it here. So X is coming from there. I think it's fine. Yeah. So we mentioned that a layer has sublayers, and we said that the sublayers are the multi-head, and we have a feed-forward network, right? So these two sublayers have a residual connection, right? So we need now to code that up. So we're gonna have a sublayer connection. You're gonna take from n.module. So module. So residual connection is always followed by a layer norm. So we're gonna say init. Oops, made a mistake here. Sorry about that. Then we're gonna take in the self. Taking the size, drop out. Okay, did I miss something here? Let me see. I think like everything is fine. Okay, so super sub layer connection. Then we take in the self dot init. Okay, then we have self dot norm equals to layer norm be size, and the size, oops, size on. Then we say self dot drop out, say equals to nn dot drop. I think it's capital letter D. Drop out. We pass in drop out. Then I'm saying def forward. We pass in the self. We have an X. We have the sublayer. So the most important thing that we should keep in note is that we want all the sublayers to maintain the D dimension, so that when we add X in the output of these sublayers, we have we can be able to add them, because if like they have different dimension, we're not gonna be able to add them, right? So that's another key thing that we should be, because when we take the input, then we have to add by the output. So hence the dimension should be maintained, which is 512 if I'm not mistaken. So we're gonna say drop, then we have sub layer, then we say self dot norm, then we take X. So so like I said, I'm gonna repeat, each layer consists of sublayers, right, which are multi-head attention mechanism, and we know that this is followed by position-wise full connected feed-forward network, right? The sublayer connection, this class is used to apply residual connection alongside with layer normalization, right? So these two help to kind of like improve the stability and efficiency of the training process. Okay, that's why we need them also. So yeah, let's look at the encoder layer. Okay, actually, you know what? Just gonna say encoder layer. Then it's gonna take from NN module. So yeah, probably you already know now. So we know that this encoder layer is made up of two things, which is the self-attention and the feed-forward. If you still, I've never explained the self-attention. So for now, every time I say self-attention, if you don't know what it is, just treat it as a black box. We're gonna get into it. Okay, so we have this thing called self-attention. You can think of it as a black box. Now we're gonna explain it in more detail. So we have feed forward, right? We have drop out, Okay, then we're gonna say super. We take the encoder layer, then we say self, we say dot unit, then we say self dot attention is gonna be equals to, no, I made a mistake, it's supposed to be self attention, close. It's gonna say attention equals to self attention. We take self dot feed forward equals to feed forward. Yep, I think it's fine. Then we're gonna say self dot sub layers. Okay, sub layers, which I'll also explain, equals to sub layers equals to clones. We take in the sub layer connection, which is this component right here. Okay, so we pass it the size and the drop out and 2. So here we will see how these are sub layers, right? We know that we need to, yes, we have 2 here because it is the attention and the feed forward. So now we need to pass those sub layers inside here. We need to insert them inside here. So how do we do that? We create this function forward. So we need to essentially, you need to apply those 2 sub layers to the input. So we're gonna have self x, we take in mask, so we have x equals to x equals to self dot what do we do, call it sub layer, right? Sub layers. Then we'd say the first we created this thing here, so we're saying at the first position we want to have attention, right? So we say x lambda, oops, we're saying x lambda, then we say x, we apply the self, we call it self attention, we have x mask. Treat this as a black box, and these parameters we're gonna explain them. So this, it's a component on its own, so so it needs its own section. So that's why I'm saying for now treat it as its own section. We're gonna get into that. So now what you can think of it is that we have 2 sub layers within a layer. Like I've been saying this, it's multi-head attention, and we have a feed forward. So here what I'm saying is that within the sub layers that we at the position 0, we add in this attention, and then at position 1, yes, at position 1 self dot sub layer is doing the same thing, just that now I'm saying at position 1 we want to say x self dot feed forward, right? That's what we apply, feed forward, yes. Okay, so yeah, it's 2, but in Python we started indexing it 1, 0 and 1, so it's 2 things, 2 sub layers, and that's what the encoder layer does. So now we kind of like wrapped it up with the encoder portion. So let's go to the decoder. So looking into the decoder, I'm gonna create, I feel like now we have the same, so the components are the same. So the decoder, its code is similar to the encoder, slightly different, but I'll explain why it is different. So we have self, taking the layer, we have n, we're gonna say super, we have decoder decoder, and we have self dot init. Okay, we say self dot layers, yes, because we have to apply the clones, which is layer, and we provide how many times we have to replicate the layer within the decoder. Then we say self.num, then we apply the num. So you see, the next part is that we're starting to reuse the functions that we have already written. So layer num, then it's going to be layer size. So here, what we need to do is that we need to say def forward. So what we take in, we're going to take in x, which is the input, then the memory, then we take in the source mask, okay, then we take in the target mask. So let me explain these things again. So x essentially is the input sequence that the decoder is trying to generate or predict from. So it's typically the target sequence in machine translation task, okay. Then we have the memory. So this is the output of the encoder component, right? You still remember from the diagram that I showed you, is that I showed you that the decoder output that continuous representation, then it goes into the decoder, right? So yeah, so the encoded representation is the source sequence to the decoder. Then the decoder uses this memory to generate the target sequence, okay? Then what do we have? We have the source mask. Yes, so the source mask essentially is a binary mask that is used to mask certain position within the source sequences from the memory, so that this prevents the decoder not to use certain parts of the source sequence. Then the second thing we have here is the target mask. Yes, the target mask is the binary mask also, but that is within the decoder, so it masks out certain position of the target sequence in the X tensor. Okay, I hope that kind of like makes sense how this works. So I'm gonna say for layer in self.layers, because we did clone this multiple times. So we're gonna say x equals to layer, then we pass in the x, pass in them. So let's go up. We still remember this code right here. Where is it? So we had memory, source mask, target, and target mask when we started. So here we're providing memory, we're providing source mask, we're providing target mask. Then when we're done, we just need to return the self.num of x. Okay, hope this makes sense. So let's look into the decoder layer. Okay, so we're gonna say class decoder layer. So we have, so the decoder layer essentially is similar to the encoder. So we have residual connection, we perform multi-head attention over the output of the encoder, we introduce another sub-layer in the decoder, which is the multi-head attention. Yeah, so what I mean here is that if we look at the architecture, so we have this first mask multi-head attention, then we have another multi-head attention which takes the output of the encoder, then we have this feedforward. So we have these three sub layers within a layer. Okay, so that's what I was saying, but anyway, don't worry, you're gonna see this inside here as I'm coding through. So we kind of take and then the module. Okay, then what we do is that we initialize this def we say init, we take in the self, we take in the size, we take in the self attention, we take in the source attention, which is coming from the encoder, and the self attention, I think it's coming from the decoder. Then we take in the feed forward, which is another sub layer within the decoder. Then we say forward, then we have a dropout. Okay, then I say super decoder. Okay, decoder layer. We take in the self, say dot init. Yes. So we say self dot size equals to size, self dot self attention, self attention. Then we have self dot src attention, which is source attention. Okay, then it's gonna be equals to source attention. Okay, what's next? We have self dot feed forward. Feed forward equals to feed forward. Okay, I think I made a mistake here. It's supposed to have an R. So yeah, I think it's fine. So we have self dot sub layers, right? So self dot sub layer equals to clones, right? So we know that each layer, yes, each layer has 3 sub layer within the decoder. Okay, so which means that we're gonna create the residuals. We're gonna provide the size and drop out, but we have to pass in 3 here. Okay, because of those 3 sub layers. And how do they work? How do they work? So this is how I'm showing you now. We're gonna take in the self X, we take in the memory, we take in the source mask, we take in the target mask. Okay, what's next? We say M equals to memory, which is, I think it's coming from this encoder. We say the first thing that we're gonna do, the first is the mask multi-head attention. So we're gonna say sub layer, which is 0. Then we say X. Okay, lambda, taking X. Then we say self dot self attention. Okay, then we say X target mask. I told you about the self attention. You're gonna understand what these X mean. For now, like I said, treat it as a black box. This is a very cool component, but yeah, we're gonna discuss it in more detail. It's quite lengthy, so hence it has its own section. But for now, just know that it works within the multi-head attention sub layer. So that's where it is. Anyway, so we have the second sub layer, which is going to be self dot sub layer, right? So what do we have on the second sub layer? We have another attention, right? Because we have to insert those input from the memory of the encoder. So here I'm expecting to see, taking the X, but I'm expecting to see that we take that X, I'm expecting for us to take the self dot source attention. Yes, source attention, which is the attention that is coming from the encoder. Then we say X memory, then we say source mask, right? That's certain things that we don't want the decoder to see. Then we say now we taking the last the last layer, which is the feed forward. So we're gonna say self dot sub layer. So 2, which is x, so which is self dot feed forward. Okay, yes. So which means that actually on the decoder I'm realizing something, which means that this generator is treated as a single thing. It's not necessarily a sub layer. So let's go to the architecture. I'll show you what I mean. So you see, these are sub layers, right? 1, 2, 3, right? Then this generator here, this is treated as a standalone thing. So it's the final thing that we output the probabilities. So it's that generator that we spoke about. So I wanted you to say, the reason I'm explaining this is because when you look at the architecture, you might think that, oh, is the generator part of the sub layer or what, right? So I want you to know that this is a standalone thing. Okay. I did explain the purpose and what is it for and what it does, right? So yeah, I think this is the decoder. So now let's look at another component. So I have been talking about mask, right? Some of you might be asking yourself, what is mask? Like, what does it work? What do you mean when we say we're applying mask? So the intuition behind here is that, like, when we on the decoder side of things, we want the decoder to use previous like tokens to predict the next token, right? So we don't want it to see the future tokens, so to speak, right? So we want it to see previous. So we mask the future, guys. So from the code, what we do is that we have this function called subsequent mask, and I'm gonna explain everything here. Which we take the size, okay, then we say attention shape equals to 1 size by size. Did I miss something? Why is it giving me, okay, it's not an error, so it's fine. Then we say subsequent mask equals to touch dot preview, which I will explain now. Touch dot once. Then we apply the attention shape. Then we're gonna apply this function also, diagonal equals to 1. Diagonal, don't worry, I'll explain everything here. So we say dot type, we have touch dot u int, states int 8. Okay, so essentially here we can think of this as let me just try to scroll down. So we can think of, like, we have a set of a matrix like so, right? So if we create a matrix of ones, right, we're creating a matrix of ones, so we can think of that trinu function. You know that function, I don't know if I'm pronouncing it well, but yeah, that trinu. So it's going to mask this if we apply that diagonal thing also. So it's going to mask this, whereby here we have, I think, zeros, if I'm not mistaken. Then here we have ones, right? But the idea is that essentially each row, right, each row represent the position of the current weight, right, while the column represent the position of the weight in the output. So essentially the model can only see one here, but these ones have been masked, right? In the next sequence it can only see these two, but these ones have been masked. In the next day it can see these three, but these ones have been masked, right? So this triangle, like they call it tree, I think, yeah, it's triangle because of this triangle shape here, so that's why they call this torch triangle, right? This is my assumption, I'm thinking that's why, but yeah, it creates this thing here, triangle. So yeah, but that's what it does. Then what we do is that we say torch dot one, okay, then we apply this according diagonal and make sure that this is an int, so, in ones. But that's what it does, and that's the intuition about masking. And when we apply masking, we're gonna apply this function that we just created now. Okay, hope this kind of like give you more perspective. Okay, now we need to talk about attention. So before we kind of like get into the theory and the maths behind attention, I want us to kind of like have a high level overview of why we need attention. So if, let's say you have a sentence, and along the, let's say you have a sentence, you're probably talking about robot, and along those lines, you refer to that robot as an it, right? But how will the model know that it refers to that robot that you were talking about in that sentence? With attention, we try to achieve that. We want to know the importance of weights with respect to other weights, right? So for instance, another thing we can look into is you can have two sentences. The other one is talking about bank in terms of finance. You can be talking about river bank. These are two different contexts, right? So bank could refer to finance, bank could refer to river bank. But with attention, we can actually be able to understand that when you're talking about riverbank, you referring to like bank and rivers and stuff like that. And when you talk about bank, we do understand that you're talking about finance, because we essentially look at, given a word, we look at the attention, we attend to other words with respect to given words. So this way, we get to understand the importance of other words for the current word that we currently attending to. Okay, but the question is, how do we do that? So this is what we're gonna get into now, right? So the first step is that we create a vector for each input. So we need to embed, right? We need to embed each word. Okay, so for each word, we create what we call query. We create key and v value vector, right? So let's say, for instance, we have input, right? What can I say? I'm gonna say transformer. So this is our sentence, transformer. This is another word, architecture. Okay, then we have this component here called embedding. Okay, so we're gonna embed this. It's gonna be x1, right? So you can think of this as a vector, x2 vector. So for each word, we create query. Okay, we created this query, so it's gonna be q1. Okay, and then we create key vector. These vectors essentially help us to be able to kind of extract context. Okay, just stick with me for now. So we have query, we have key, then we have value. Okay, we're gonna say v1. Okay, then what we do is that we initialize, yes, we initialize a trained weight, right? We initialize the train weights of query. So we have wq weights, oops, then we have another train weight which is wk, right? So these are learned during training. Okay, so we learn these during training, and essentially we take this x, we multiply it by this weight, then we create a query. We create this query, we take this, we get this key. Okay, then what we do from there is we calculate the score. Okay, we calculate the score. So we take the query, yes, we take the query, we multiply or do a dot product with the key, right, q1. We get q1, do a dot product, we attend to other weights. So the key for this weight, right, is going to be q2. Let me just write this. So here you can think we have q2, sorry, q2, because it's the key and query for this weight right here. Okay, so we take, essentially, I'm just going to do this. So we focus on the first weight. So we take q1, multiply by q1, q1 multiplied by q2, just like that. If we had multiple weights, then we're going to say q1 multiplied by q3, right? Before we move on, I just want you to understand that we are doing this transformation for only one weight, right? So that's hence we're taking q1 multiplied by k2. So we're gonna do the same thing. Yes, we're gonna do the same thing for the second weight. So you can think that we're gonna take q2, which is coming from the second weight, we're gonna multiply by k1, q2 multiplied by k2, just like that. So for now, I'm only using weight 1 because it's the same transformation. We don't have to do it for all the weight, but hence I drew this thing here so that just know that we're doing this transformation for the first weight, right? But essentially we do this for all the weight, and the same thing we're gonna repeat on other weights. Okay, so anyway, here we calculated the score, which is a dot product. Why do we do that? It's because we want to measure the similarity between the two vectors, right? So that's what we do. Then the second thing that we do is that we try to divide by the square root of the dimension of k, which I think it was 64 if I'm not mistaken. So why do we do this? It's because we want to stabilize the gradient, right? We want to stabilize the gradients. That's why we have to divide by the square root of dimension of k. So k is this component right here. Okay, so then we go to the next step, whereby we try to take the score. You can think of here we got the score of maybe 41. Then we apply the soft max to this. Why do we apply the soft max? It's because we want to normalize the scale so that they all add up to 1, right? So it helps us determine how much each weight will be expressed. So we apply the softmax here. So all of these add up to 1. So we can imagine that the first weight attended to itself, so hence the score is high. And the other weight maybe is going to be 12, something like that. So, but that's what we do there. Then the last step is to take this score that we just got and we multiply it by the value. So I'm just going to change the color, just going to select white. So we take softmax score, multiply this by the value, and we get v output v2 output, right? Then we sum all of these things, to get the output. Okay, so we sum all of these things to get the output. So essentially, why do we do this? It's because keep the value intact, right? We keep the value intact so that we can kick out all irrelevant weight, or the weight that have very so for example, let's say we have a value here and we can multiply this by a very small score that we got here after softmax. So for example, let's say we multiply this by 0.0001. So this, it's going to be irrelevant, whereas we multiply this by a very big score here, 0.88. So this is going to be big. But the point here is that we kick all irrelevant weight, which are not, remember that I told you about context, right? So which means that maybe this weight does not have more context, does not have any context to this current weight. So that's why here we multiply softmax by value. But that's the intuition. The intuition is the most important thing. As long as you understand the why part, why we're doing certain things, I think that's what is important. If you still don't understand, don't worry, we have to code these things up. So I'm gonna repeat literally the same thing that I said. So yeah, when you see this from code, maybe it will make sense. So now let's code the attention. So if you didn't understand my explanation of the attention, it's okay. I'll explain it again with code. So what I'll do is that I'll create this attention. So we said that we take in the query, right? We have key, we have value, we have mask, okay? And when this is none, we have a dropout, okay? And let's continue. Oops, it's complaining. Yes, that's because of you're not supposed to have these parameters before, after default parameters. So it's either gonna have to make this one a noun, and it should be fine. Anyway, so the first step we need to do is that we need to calculate the dot product of the query and key matrix, okay? Then we said that we're gonna scale it by dividing this by the square root of the key dimension. And we said that we're doing this so that we prevent the dot product from getting too large, okay? So we need the key dimension, so we can use the query dot size, which is going to be this one. Then what we do is that we take the scores. So we said that we take in what? We take in the query and the key, so it's going to be multiplication, then we take in the query, okay, we take in the key, but we need to transpose it, then we're going to say that, then we divide this, as we said, by square root of the dimension of k, okay? Still makes sense, right? So mask sometimes is optional, okay? Sometimes can be given, sometimes not. But if mask is not none, right? So we need to apply mask to the scores. So we're gonna say scores equals to scores dot mask fill mask equals to 0. Then we're gonna say -1 2. So the question is, I'm gonna repeat this. A mask is used, right, to prevent the model from attending to certain position in the input sequence, okay, such as padding tokens. So where the mask is 0, so we don't attend to that. So this can also be applied in the encoder, so just to know that. So that's why if we have to mask, so we have to do that. Anyway, then what we need to do now is to apply the softmax, and Why did we apply the softmax? It's because we produce the probability distribution that indicate how much attention should be placed on each position of the input sequence. Okay, so what we do is that we say p attend equals to scores dot softmax, yes, softmax, and we say dimension equals to 1. Okay, we can apply drop box if drop box drop out. Why am I saying drop box? If drop box is not none, right, then it's fine. We can actually apply it to prevent overfitting, right? That's why we do this. So drop out p attention, then we return. Remember that we said the last thing is just to multiply the score by the values, so dot multiply p attend by value and return the p attention. Right? Hope you have a sort of like an idea, even if maybe you're still trying to get the attention and maybe understand it in much detail. I'll leave some links so that you can kind of like understand it much better. I think I leave some links, some beautiful links. Someone could have explained it better. But yeah, I think the most important thing is the intuition, why the author had to do this, and yeah, I think that's what I think is more important. But anyway, let's continue. So the author did actually try to refine the attention more further by introducing what we call a multi-head attention. So the intuition behind the multi-head attention was that it actually enabled the model to focus on different aspects of the input data. Then these heads, they actually produce output, and we combine those output to get a better representation of the input data overall. Not only that, but the author did actually try to test the performance of the model, and they realized that actually multi-head does produce better results compared to using a single attention. It could be that using a self-attention only alone, maybe some of the weights that we're attending to currently could be dominating the other weights. So that might be why we want to use the multi-head attention. Okay, so let's take more of a theoretical approach and try to understand what's actually going on with the multi-head attention. So, looking at the multi-head, which I said that the main goal here is to expand the model ability to focus on different positions. So the attention layer acquire multiple representations of space, right? So that's what the multi-head attention was designed for. So essentially you can think of this as like we're still doing the same thing as we did when I explained the attention, okay? But this time, if we have our input like so, x, and we're gonna say that, let's assume that our sentence was transformer model, okay, this represented as a matrix. We can have the first head. So we can have the first head, let's say head 0, okay. On the head 0 we still have the query 0, and we have query weight 0 of query, and we have also weight 0 of key, right? We still have the key 0, we still have the v 0, so we still have q, k, v, okay. Then we're gonna have the same on header 1, so literally we're gonna have the same on the head 01. So you can think here we have q1, q1 and v1. Similarly, we have the weights for these components, and we can all have all of these heads all the way up to head n, okay, head n. So within these heads we still apply the attention mechanism. right? So we spoke about that tension. We know that with a softmax, right? So we said we take the Q, we do a dot product with the K transpose. We apply the square root of K dimension, KD dimension, then we multiply this by V. So you can imagine that each head essentially is gonna have the Z. That's what we said the output is gonna be, right? So we're gonna have Z1 all the way up to Zn. However, the dimension of the concatenated output from all the head will not be the one that is expected from the second sub layer. So what we need to do is that we need to somehow be able to get the right dimension. So what we do is that we introduce another weight, right, which is trained also along during the training. We also update the weight for this, so we can think of this as W0. Then what we do is that we multiply the output with that weight. Okay, then we get a single Z, which is the single Z output. Okay, and that's what it works. So there's more into it, and like how we apply linear projections and all of those things. So I decided to explain those in the code, but I just needed to give you a high level overview of like how it works at the high level. But this is essentially the multi-head, so it's still the same, just that with different heads. And some of you might be like, don't you think the computation now will be expensive because we have head here, you have another head here? So essentially each head, I want to make sure that you understand this, each head, we take the dimension of the model, then we divide by the head, by the number of head, I think. So this will give us maybe 64. So the dimensionality will be smaller of each head. So the computation will be the same as if we're applying one head or maybe one self-attention. So in terms of computation, we still get the same because of each head essentially gets a small piece, just like so. But anyway, I think I'll actually explain more things better if I get into the code. So without wasting any time, let's code this up, and I'll actually be explaining each line and the intuition behind everything. So we have class multi-head attention, then take nn.module, we initialize def init, we take in the self h and d model, then we say drop out equals to 0.1. So head and dimension of the model. So we say super. Okay, then we take the multi-head attention, and as always self dot init. Okay. So we say a set just to make sure that. So this is to make sure that the model is divisible by the number of heads. So we're just gonna say model dimension head has to be equals to 0. Then we're gonna say self. We're gonna be set for dk equals to d model modular h. Then we assume that dv is equals to dk. So self dot h head is going to be h head, which is self dot linear linears equals to clones of nn dot linear d model, and d model provide 4, so we have 4 linear layers. So that's what we have there. Self dot attention equals to none. Then we have self dot dropout regularize. We're gonna say nn dot drop out p equals to drop out. Okay, then we have the forward pass, which we're gonna take in the self, the query, the key, and the value, and the mask equals to none. So before we continue, let's kind of like take a step back to remind ourselves. So like I said, that each head, right, each head uses a small subset. So we can think of like here we're taking the model, we divide by head, number of head, then we get I think 64. So we're using a subset of the entire model dimensionality for each head. So another thing that I think we should keep in mind is that instead of each head focusing on the entire sequence, rather we focus on the subset of the input. So this enables the model to focus on different aspects of the input data, right? So instead each head focus on a subset of input feature rather than all of them, right? This allows each head to have like an aspect like of each input data. So when we combine this, the model has a more robust understanding of like the whole entire input sequence. So I know I might be confusing you here. Okay, let's take for instance. Imagine we have 8 heads, right? Like 8 heads, and the input sequence is 10 weights. So let me make an example here. So we have 8 heads, and we have 10 weights, right? Each head will look at the different portion of the input sequence. For example, head 1 will probably look at maybe 1, 2 weight, then head 2 will probably look at the 3, 4. Okay, just like that. So that's what I mean. So now what we need to do is that we need to continue with gonna start with the mask. So we're gonna say if the mask is not none. So in the encoder, the mask can be optional. So we can say mask dot unsqueeze dimensions unsqueeze equals to 1. Then we say n dot batches equals to query dot size. Then we're gonna have a linear projection. I think what happened? Did I make a mistake here? And batches, let's see, n is not defined. Okay, no, I made a mistake. Number of batches. So we're gonna say 1 to apply linear projections, right? So we're gonna say query key value, then we say equals to this, then we say len x dot view of n batches, then we take n minus 1 self head, then we say self dot dimension of key, then we transpose this, this. So this is a least compression function, so that's why this is not there. So we're gonna say for L and X in zip self dot linear, then we take the query here. So I think I'm just gonna do this linear, then we have query, we have key, we have value. The next step is to apply attention on all the projected vectors in batches. So we're going to say x self dot attention equals to the attention function that we created. So we give it the query, we give it the key, we give it the value, we give it the mask equals to mask, we give it the dropout equals to self, the define self dot dropout. Okay, that's not an error. So that is step 3. We concat using a view and apply the final layer. So pretty much what we're doing is this component here. So this visualization that you see here, that's what we're coding here. We concat using a view and apply the finalization. And say x equals to x dot transpose, and we say dot contiguous, it's all US, I think. Then we're gonna say that dot view, we take the n batches, then we're gonna take the self dot h multiplied by self dot dk. Then we can delete the query, and we can delete the key, and we can delete the value. Then we return self dot linear minus 1 x. Okay, so that's that. The intuition behind this code is that it's preparing the input and the key value tensor for the attention calculations. Okay, that is what we're doing here with the linear projection. So the linear projection essentially creates multi-head attention of mechanism where each head is looking at different aspects of the input, right? The reshaping and transposing of the tensor make sure that they have the right shape of the attention calculation, which will be done in the next step. So that's what this code does. I hope it kind of like gives you a better perspective of what's going on. So the next step we're going to look into is the positional encoding, which is another important component of the transformer. Actually, before we go to positional encoding, I think let's look at the second sublayer. Remember that we said that the encoder has 2 sublayers. So it has like the first multi-head attention that we just coded up here. Then it has the position-wise feed-forward. Just to remind you of that. So we have multi-header here, then we have the feed-forward, right, as the second sublayer. So what I'm saying is that let's code this feed-forward. So they're calling it position-wise because it takes the position, it takes the output in parallel, right, from the multi-head output. Okay, so it's going to be feed forward, then we're going to pass in the module. This will be fairly quickly, so we're going to say init, yes, then we take the self, then we take the dimension of the model, we take the dimension of the feed forward, take the drop out. We're gonna make sure that default is 0.01. Then we're going to say super take from position. Actually, to avoid making a silly mistake, I'm just going to copy this, and as usual, just take itself dot init. Then we define the first weight. So it's going to be weight 1 gonna be equals to nn dot linear. Then we're gonna take in the dimension of the model, then the dimension of the feed forward, then the second let, that means it's gonna take the feed forward dimension, so it's gonna be weight 2 equals to nn dot linear. Then we're gonna pass the ff, then here the model, then we apply self dot in the activation function. We're gonna apply it in the forward pass. That's fine function. So now we can just actually define the dropout, which is gonna be nn dot drop out. Then we pass in the drop out here. So def. Then we pass in the forward pass, which we know is gonna take in self because we need to use those functions. Then we're gonna pass in an x, which is the input. Then we're just gonna have to return. So we know that the first layer is gonna say self dot weight 1, right? Then it take an x. Then after that we have to apply the ReLU activation function. Then after that we apply the drop out. Then we say drop out. We've covered this. Then after that we take these output, we pass them towards the weight 2, just like so, right? And we're done. So now positional encoding. Positional encoding can be quite hard to wrap our head around, so I thought it would be good to kind of like walk you through the theory of it. It's quite interesting how they kind of came up with it, but yeah. So essentially, weights have to have some sort of like a position, right? However, how for the model to understand that, okay, this weight is at the first position, the second weight is second, the position can be hard. So how do we account for the order of the weights in the input sequence? So that's when we introduce the positional encoding. So essentially you can think of like this, né? We have input, like let's say we have the car, something like that, né? We know that we embed these two, né? Then we apply position. So it's like, think of we're adding a vector. So these allow the model to learn the position of the model, right? So we add these positions. So that actually allows the model to know that this is the first weight, right? So some of you might be asking yourself, why don't you just add indices like 1, 2? Isn't the model gonna not know? Because we're working with matrices. So essentially indexes can grow, especially if your sequence is very large. So the magnitude can grow very large, so it can actually affect your model, so in a way, so you don't want that. So that's why we're gonna talk about how they come up with some of the techniques here. So let's go to the code. I'll explain their techniques and how they implemented this. So the author used the cosine and sine function to generate the position encoding, right? The idea behind the cosine and sine is that they produce unique representation of the different position in the sequence, right? And the cosine has a repetitive repeating wave function that can represent the strength of the position, whereas with the sine it is a repeating wave, but it's shifted towards, I think, 90 degrees if I'm not mistaken. So yeah, that's why they're using these functions. I can't wrap my head around them that much, but I have an idea how they work. But yeah, at first also it was quite difficult to kind of like understand, but yeah. Anyway, let's code it up, and I'll explain the code in a much clear way. So we have class positional encoding, then the end.module def def init, taking the self dimension of the model, we're taking the drop out, we're taking the max length, which is 5,000. So taking the super. So I think the max length, essentially we create like what is it? We create positional encoding. We firstly initialize it. So we make sure that it has the length of 5,000. I think the row has like 5,000, then like the column has the size of like the dimension of the model. So we initialize this with the 0. So I'll show you, but that's what this max length is going to represent. Just know that. But yeah, when we get there, you'll see what I'm talking about. Anyway, we have positional encoding. Then we take the self, the dot init. We say self dot drop out. We say dot init dot drop out. Then we say p equals to drop out. So this is what I'm talking about. We're gonna say, so we initializing a zero tensor, called positional encoding of size max length by the dimensional modality. So we're gonna be positional encoding equals to touch dot zeros. Then we take the max length. Then we take the D model. So the second step, so we're gonna create a tensor position of size length also. That is going to store the position of each token in a sequence. So we're gonna say position equals to touch dot arrange mix len dot unsqueeze unsqueeze, then do so. Did I make a mistake here? I think I did. Okay. Then we say div temp equals to touch dot expand, and say touch dot arrange. So it's one arrange. Then it's 0d dot model 2. Then we say multiply by negative maths dot block. So say 10,000. So divide by the model. Then we take the PE it's going to be touch dot sign position by dividing temp. I'm going to say PE equals to, just do this. Okay. Did I miss something? I think that's fine. I'm gonna say equals to touch dot cosine. Then we take the position by dividing 10. So so I think that's fine, right? I mean, maybe I missed the comma here. I think this is supposed to be touch position. Okay. Okay, that's fine. We're gonna say PE equals to PE dot unsqueeze. Then we're gonna say self dot register buffer. Then we say PE. Then we have a final forward pass. We're gonna say self, take the input, self input, then we say x equals to x plus self dot PE. So we take x dot size. Then we say dot requires grade. I'm going to say false. And we return self dot drop out, which is x. So yeah, I think I have everything in place. Okay, cool. So that's like how the positional encoding is coded. So the author experimented with using the length positional embedding instead, and found that the variant of two different positional encoding were identical. So they chose this since they're calling it sine and cosine vision, because it allowed the model to extrapolate to sequence length longer than the ones that they encountered during training. So that's why they went with this. So you just keep that in mind. Other than that, I think these are all the components that we need for the transformer. So I'll share all my materials that I used for this, for all of this information, so that you can dive deeper if you want to into this, if I didn't clarify certain component. So probably I'll list some resources for you guys to kind of like read on the transformer architecture. So in the next video, I'll try to now cover the training part, and how this was trained, and go through the code also. I'm still new to YouTube, so I'd like to get your feedback, and hopefully as time goes by, I'll improve on my explaining abilities. Other than that, thank you for watching up to the end.